Hello everyone, and thank you so much for enrolling in this course. I want to take just a few minutes here to go over the course curriculum. So welcome to this free course on the Gemini Python API. It's really meant just to be a quick start guide to using the Python API for the latest Gemini AI model from Google. Before you continue on through the course, please keep in mind a few things. One is the prerequisites on the landing page. So we're not going to teach you absolutely everything from scratch. There are some experience requirements. Basically, you should understand some basic Python, like the ability to create your own functions and understand things like how to install libraries using pip install. Keep in mind, you'll also need a Gmail or a Google account to actually create your API access key, and that may be limited in certain countries. So I just want to point that out now. Of course, that could change in the future, but keep in mind, certain countries are restricted on creating things like a Gemini API key. That's really outside of our control. That has more to do with Google. I also want to note that in order to keep this course free, we are limited to only 2 hours. So we're not going to be able to cover absolutely everything you can do with this model, but we are going to try our best to give you a really great head start using this course. So what are we going to cover in this course? First, we're going to give you a very high-level overview of understanding how large language models, or LLMs, work, and we're going to dive in slightly deeper than most other courses so that you can understand how the probability distribution and sampling of tokens works, because that's going to be important when we talk about configuration parameters later on. And then in the lecture after understanding LLMs, we'll show you how to obtain API access. Again, keep in mind that certain countries are blocked from using Gemini. So then we have our text generation section of the course. Here we cover a couple things, just general text generation. So if you provide a prompt, how do you get some output out? Then we'll discuss the Gemini Pro's capability to create chat models where you have an ongoing message between the user and the model and can access history of that chat. And then we'll talk about configuration parameters. So if you've heard about things like the temperature of a model or using things like top K or top P, we'll go over those configuration parameters and how to best use them along with a little bit of prompt engineering to adjust the model's outputs so you can get exactly what you want out of the Gemini model. Then we'll have a quick discussion about the vision version of the model and multimodal inputs. It's actually pretty straightforward. You just need to know how to read in an image, and then you can provide an image to Gemini along with text for multimodal input, so you can actually get the Gemini model to use that image to perform actions. For example, we're going to send it a picture of our refrigerator and then ask it questions like, make me a recipe from what you see in this picture of my refrigerator, or let me know, do I need to buy tomatoes at the grocery store based off this picture of my fridge. And then we'll end the course with a really interesting topic known as RAG, or Retrieval Augmented Generation. This is where we really take advantage of the model's capabilities to perform embeddings, and then we can use that with our own documents to create a vector store in order to use our own documents and inject them straight into our query into Gemini without the need for something like fine-tuning. It's a really clever idea, and I'm excited to show it to you towards the end of the course. With that being said, I'm so grateful that you've enrolled, so let's get started. I'll see you at the next lecture. Welcome back, everyone, to this lecture on how a large language model works. We're going to cover how a large language model works from a very high-level overview. You should note that what we're discussing here is known as inference, not the actual training of a model. Google's already trained the Gemini model for us. Really, we're just understanding how it picks that next most likely text given some input text. Having this basic understanding of how the model works is really going to help you understand the generation configuration parameters that we cover later on in the course. Again, this is a very high-level overview. So fundamentally, when we're dealing with the Gemini large language model, or any large language model for that case, we're providing some text to the large language model, and then we get some output text. So really what we're trying to answer is, how do we go from our input text to the output text? What's happening inside this Gemini large language model? Well, first thing is to understand the model doesn't think of words like you and I do. Instead, it takes the input words and breaks them up into what it calls tokens. This process is known as tokenization. You'll see here that larger words are broken down into smaller tokens. This will help with different things like prefixes or suffixes, or just understanding different parts of languages. So for example, the word capital might be broken up into two parts, cap and then idle. So Once we have the tokens, the trained model is going to convert those into what are known as vector embeddings. Clearly, there's a lot of math going on inside of the Gemini large language model, and you can't multiply or divide words. You can't say something like, what's France divided by Paris? So in that case, we're going to need to have a mathematical representation of the tokens. So we're going from words to tokens, and then tokens to mathematical vector embeddings. The creation of these vector embeddings is part of the training process. So once we have a trained model, we can directly go from words to tokens to embeddings. Understanding this part is important because later on, we're just going to use this half of the model, so to speak, to perform what is known as RAG, Retrieval Augmented Generation. Now, in terms of text generation, once we have the vector embeddings, we're really asking the transformer model, what is the next most likely vector given this sequence of vectors? Which kind of makes sense. We're going from words to tokens, tokens to vector embeddings, and then I'm just asking the model, if I gave you this series of vectors, what would you say is the next most likely vector to occur? And then I could just work backwards from the vector to the token, and then the tokens to the words. The key thing to keep in mind, however, is the transformer model doesn't just think of things in a deterministic fashion, that there's only a single vector that will show up here. Instead, it creates a probability distribution of the next most likely tokens. Something to keep in mind is it's technically thinking in terms of vectors. So after performing some mathematical operations internally, at the end, you're getting a probability distribution. And then we're going to sample from that probability distribution to get the vectors. But remember, the vectors are actually just tokens that can always be transformed back into words. So we can see here that if I were to sample from this probability distribution, I would maybe have a 95% chance of choosing the token vector embedding that was connected to the word Paris. And then I would get the output of Paris. This is kind of just a made-up extreme example. If you were to ask the model what is the capital of France, and you were to take a look at the true probabilities, you would probably have something like a 99.9% chance of Paris being the next word. But if you're doing something more creative, like asking for a poem, then there's going to be a kind of flatter distribution, and you're going to get more creative outputs. Because remember, you're not necessarily choosing the most likely token. You are sampling from this distribution. So in this kind of made-up case, you could have had a 2% chance of picking Versailles. Maybe that's because Versailles was a historical capital of France. So it's not necessarily guaranteed that you're always going to get the next most likely token. Later on, we'll see that there's configuration parameters we can set to actually change and play around with this distribution, because maybe you want to pick less likely tokens to get a more creative output, or maybe you always want to pick the next most likely token. Key idea here is that you're creating a distribution that you sample from. And then you can work backwards to the vector embeddings, to the tokens, to the words, to get back text generation that we as humans can understand. So what are the key takeaways that you should know? You should understand that the model internally is using tokens and not words. And the model has its own internal vector representation of these tokens, known as a vector embedding. And that the next most probable token is chosen from a distribution. That allows for what is known as stochastic results. That is to say, the next token is not guaranteed to 100% always be the same. In other words, it is not a deterministic process. Even for the exact same input, you can expect to get different results because you're sampling from a distribution, and that can cause changes further down the line. So if I asked for a poem, I would probably get different poems even if I provided the exact same input. Later on, we're going to explore configuration parameters and what's known as RAG with embeddings. So we can actually take advantage of the model's ability to embed words to vectors for what is known as RAG, Retrieval Augmented Generation. We can also edit what are known as configuration parameters. For example, we could change how we create the probability distribution for the next most likely token. All right, with that being said, let's get started and set you up with an API key to access Gemini. Welcome everyone to this lecture where we're going to cover how to get API access to the Gemini models. To begin using Python to access the latest Gemini models, we're going to go to ai.google.dev that has information about how to go to MakerSuite to actually create the API key, as well as just information about the Gemini models. I want to quickly point out, however, there are technically two ways to access the Gemini models. You can use an API key in Google AI Studio, which is what we're going to use, but you can also technically use the Vertex AI via Google Cloud. So Google Cloud already has hosted large language models like the PaLM models, and they've had that for a while. meaning it also has access to more advanced I am capabilities for access management. This basically just stands for Identity and Access Management. We don't actually cover this approach in this course, but if you have some experience with Google Cloud, for instance, you've already set up things like Credential, IAM Access, and Google Cloud, you can go to this link shown here to understand how to access via Google Cloud. Again, I would really only recommend this approach if you've already used some other Google Cloud Python software development kit, since it does require creating a Google Cloud account, creating an IAM profile, and downloading JSON credentials for that account to have Vertex AI permissions to then access the Gemini large language models. A much simpler way of accessing the models is through an API key. So, Google has an easy-to-use Google AI Studio that's located at makersuite.google.com. We'll actually see that when we go to ai.google.dev, it basically has a link that takes us to the Maker Suite. And then this studio contains both an API key creation center as well as a graphical interface to quickly test prompts. So let's continue on by going to ai.google.dev. Keep in mind that this overarching URL may change in the future. You may just want to confirm with a quick Google search like Google AI Studio or Google Gemini API key to get to the right link. Keep in mind that may take you straight to the Maker Suite, which is actually where you create the API key. Also, make sure to check our notebook for troubleshooting links and other helpful information regarding the API access. So I'll go to ai.google.dev so you can see that before we actually create the API key in the Maker Suite. Okay, so here I am ai.google.dev. Keep in mind, it's very likely that this page will change in the future, at least what it looks like. But somewhere on this page, you may find the link to get API key in Google AI Studio. If you don't see that link, you can just go to the URL yourself. The URL is makersuite.google.com. But if we really want to just quickly check out ai.google.dev, it has information about the 3 Gemini models. Currently, only Gemini Pro is available for general use. Ultra, the larger model, is coming later on. And then Gemini Nano, the small one, meant for things like try offline or on-device use cases, is also coming later on. Has lots of information about how to access via Python, Node.js, Swift, Go, other APIs, and you can scroll down for more information, as well as benchmarks, etc. There's also a nice documentation page that you can check out for full documentation on Gemini references. There's also pricing information. So at the time of this filming, for the free for everyone, you have a 60 queries per minute, where price of input is free, price of output is free. However, you do actually allow the input-output data to be used to improve or train the model, so keep that in mind. If you want a pay-as-you-go, that's actually technically not available yet via the Google AI Studio. So keep in mind, don't pass in something like your social security number into the API keys via Google AI Studio. So let's go ahead and get that API key and test it out. Now this may, by default, keep you on the prompt page. This is where you actually test out prompts, and you can change out the model. Right now there's just Pro and Pro Vision. You can also play around with temperature. We're going to learn how to do all of this with Python, but what's really cool is if you just play around with the prompts here, what you can do is click on Get the Code up here in the right-hand corner to quickly get the code in whatever language you're working with. But in order to do this and learn Python on our own, within our own development environment, what I want to show you is how to get an API key. So you're going to want to go to over here where it says Get an API Key on the left. I will click on that. It's going to ask you if you want to save those changes. I don't care. And then we have the API keys. So something to keep in mind is currently Google AI Studio limits API keys to only one active project. If you've never used anything on Google Cloud, it basically is just going to create a project for you upon creating the API key. So you should be able to, if you're just brand new to this and haven't really used Google Cloud, you should be able to click Create API Key in New Project, click on that, and then it will create the API key. If you're getting an error, such as the one down here that says, I'll get that error message again, caller does not have permission, that basically means that Google AI Studio already created a project for you and you just need to select that project. So if you've deleted a historical API key and you need a new one and you're getting that error of, hey, the caller doesn't have permission, it just means you need to click over here on the second option, Create API Key in Existing Project, and then you can search for the Google Cloud projects, but you should see that it created one for you called Generative Language Client. You could see that I had other projects there because I use Google Cloud for other projects, but it should, after you've created an API key once, have already created that existing project for you. So you're going to use the second option there. I'll go ahead and create that new API key. It's going to generate it. And then right now, you'll have the API key. Remember, you don't want to share these API keys, so that's why I have mine blurred out right now. I will go ahead and copy this API key. It should be a string of letters and numbers, and then we're going to write that down somewhere on our computer. So I'm going to go ahead again and copy this, and I'm going to head over now to my Python development environment, which is Jupyter. All right, so here I am at Jupyter. As a quick note, in the zip file from the very start of the course, we have a folder called API Access Setup that has a notebook called 00 API Setup that has lots of information about how to install the Python SDK, how to get the API key that we just discussed, as well as some troubleshooting notes that gives you really useful links to other things we talked about, as well as more in-depth information about different ways of setting your API key, as well as saving it, doing something like an environment variable. That way it's not exposed. Now, we're going to just do kind of a simpler version of this where we just set it as an environment variable using the OS. But technically speaking, in the Jupyter Notebook, that's going to get reset every time depending on how you actually installed Jupyter. So we have full details here on how to save your API keys in a more secure manner. But let's go ahead and start a new notebook and just show you how to use the API key that you just downloaded from MakerSuite. So first things first, you have to actually install the generative AI library or package from Google. So to do that, it's just going to be a pip install, and you can run that inside your notebook with an exclamation mark, pip install Google-generative AI. You can also do this at your command line. Again, however you like to pip install libraries, you're going to do that, but the library we need to install is Google-generative AI. I already have it installed, so I'm good to go. You sometimes need to restart your kernel. You can go to kernel, restart kernel, if you just installed a new library inside of a Jupyter notebook. So let's confirm that the installation worked by importing it. We're going to say import google.generative AI as gen AI. And remember, you have your API key. So what I'm going to do is I'm going to set a variable called API key is equal to, and then I'll pass in my API key there. I'm going to go ahead and just quickly paste my API key in. You'll see a jump because I don't want to share my API key. All right, so I pasted in my API key as a string, and then I ran this line. Of course, your API key is going to be different. And now I have API key. And if I check the length of my API key, it's some 39 long digits and letters. So how do I actually make sure that this is working with Google Generative AI Library? Well, of course, later on, we're actually going to generate chats and that sort of thing. But what I can do is call gen AI, and I'm going to configure it to connect via my API key. So we'll say API key is equal to API key. And if you're able to run that line without any errors, you should then be able to list all the models available. So then we can say here, for model in gen AI dot list underscore models, and then we'll say print the model name. Go ahead and run that, and you should see a bunch of models available. There are the older models available, like ChatBison and TextBison, and the three that we're going to be working with here are the Gemini Pro model, Gemini Pro Vision, which can take in images, and then later on, to show you how to actually perform retrieval augmented generation, we'll use the embedding model. But these are the three models we're going to be working with. As long as you see these three, then you're good to go. And we know that by listing these models, we successfully connected this API key. That's it for API key access. Again, I have a lot more detail in the API setup. If you want to learn how to set this up as an environment variable, you can do that at the command line or in the notebook or in your Python code, however you prefer. But the simplest way to do it is just set it up as a string. You can always delete that line and then just connect it via the configure call. If you got the list of model names, you're good to go. And let's start generating some text. I'll see you at the next section of the course. Welcome back, everyone. In this lecture, we're first going to explore how to generate text via a single prompt to get back a single result from Gemini. In the next lecture, we'll go over chat models, and then at the end, we'll talk about different parameters like temperature or top K that allow you to change the results that you get from the model. Let's check it out. Okay, here I am at my Jupyter notebook. I've already imported Gen AI, that is Google Generative AI, and I've configured my API key like we did in the API Access lecture. Keep in mind, in this lecture, I'm going to show you the single response text call, that is a single prompt and a single response. In the next lecture, we'll actually create a chat model with an ongoing conversation. What's interesting is the underlying model is still the same. So let's actually create an instance of our model. We're going to say model Gen AI dot, and then we call generative model, and then pass in the string of the model we want. Remember, in the API access lecture, we saw a list of models available. So we're going to go with Gemini-Pro. Later on, we'll explore the Pro Vision model. And so that creates an instance of our model. And then what we can do is generate content with that model with a given prompt. So for example, the prompt can be just a simple question like, what is the capital of the United States? ? And then I'm going to get a response by generating content with the model. So I will say the response object that I get back is from model generate underscore content, and then I pass in my prompt. And this is going to take a little bit of time, but for such a small, simple prompt, it should be relatively quick. So we get our response back. Keep in mind, the response itself is actually not just text. If I take a look at the response object, it's actually this special object called generate content response. So keep that in mind. If you just ask for response like this, that itself is an object that contains attributes. The attribute you're probably most interested in is the text itself. The text is the actual string that hopefully answers the prompt. So for example, what's the capital of the United States? The response text is Washington, D.C. There are other things returned, however, inside this response object. So for example, I can see there's also a prompt feedback attribute to this response. So prompt feedback has to do with the safety ratings of different categories. Depending on what you ask, it may actually trigger a moderation endpoint for Gemini, meaning it won't return back your response. This has to do with the safety of Gemini. You can see the different categories that it's going to try to stop, like dangerous content, harassment, hate speech, and sexually explicit content. So for example, you can't ask Gemini something like, how do I create an explosive device using these materials? That would probably categorize it as dangerous content, and then it would give you some higher probability and block the output. Obviously, we're not going to do that sort of thing in this course, but I just want you to be aware of that it does have these safety categories as well as probabilities. Now, in the future, we'll actually be able to ask for multiple candidates. I should point out that right now, Gemini is limited to one candidate, and we'll talk about candidates in the parameters lecture towards the end of this section. But basically what that means is in the future, you'll actually be able to ask for like multiple candidate responses and then figure out on your own which one you like best. If we check out response.candidates, you can see that we technically only have one candidate at index 0, which is the text, the role, and the role just basically confirms whose side of the text this comes from. So Washington, D.C. is coming from the model. The role is going to be more important in the chat lecture. And then we get back the finished reason, which we'll talk about later, and then the safety ratings. And that's basically it. But keep in mind, you can do things that are a lot more creative than just asking for what's the capital of the United States. I can do something like write a rap about Claude Shannon, who's kind of known as the father of information theory, and then make sure it rhymes. And then we'll get the response, and then let's ask for print response text. If we print the response text, that will actually take into account things like new lines, so it should format it for us. And so there it is. So in the realm of information theory, a legend has emerged, his knowledge surged, he cracked the code, a path untrod, mind, kind, began, man. So it looks like pretty good. Okay, as a last point I want to make here is you would probably, in your day-to-day use case, just make a simple function. So you can do something like def get response, and then you'll pass in the prompt and do something like the response is equal to model.generate content from that prompt, and then return the response text. That way you can just do it with a single call rather than having to generate the content and then grab the response text. So pretty straightforward. Again, generative model, generate content, grab the response.text. Let's explore chat conversations in the next lecture. Welcome back, everyone. In the previous lecture, we saw a single prompt for a single text generation response. Let's now explore a chat that has a historical message conversation between the user and the model. All right, here I am back at a Jupyter Notebook. I've already imported Gen AI and I've configured it with my API key. Next, what I'm going to do is create an instance of the model, just like we did last time. We're going to call GenAI.generative model, and I'm actually going to pass in the exact same model, Gemini-Pro. And then in order to initiate and tell Gemini that I want this to be a chat conversation, I need to create a chat instance by saying chat is equal to the model, and then I'm going to start a chat. And something to keep in mind that makes this different from text generation is instead of calling this off the model, the rest of the methods, I'm going to call the methods off of this chat. So if I take a look at what chat is, it's this chat session. And the chat session will then record a history of messages that are back and forth between me and the model. And that's nice because I can refer to historical messages without needing to restate everything every single time. Let's show you an example of what I mean by that. I'm going to get a response, and to send the message to the model, I say chat send underscore message, and here you can provide your prompt. For example, help me plan some activities for my trip to Paris. I go ahead and run that, and just like before, I can grab the text response by saying print response.text. And I can see it tells me to visit the Eiffel Tower, explore the Louvre, take a stroll, visit Notre Dame, etc. So, because this is a historical chat conversation, that means there's actually a chat history. So I can say chat.history, and it's going to have a recording of the different parts. And what's interesting about this is it understands the text that the user sent. So notice there's now this idea of a role for the user here for this text, as well as the text that the model sent. So the role of model indicates that the model returned this text, and the role of user indicates that the text was returned or basically sent over by the human. So what's nice about this is I can keep the conversation going simply by sending another message. So I'm going to comment that out, and we'll explore that chat history in a little more detail in just a conversation. But what's nice about this is I just keep the same response going. So I can say response is equal to chat.send underscore message. And then I can refer to something from the history by just saying, give me more detail about your last point. So notice I'm not explicitly saying that I want to check out these Lafayette galleries. Instead, I'm just asking for that last point. And because it has a history, it understands the context of what I mean by that. So let's print out now the response text here. I'll go ahead and run that. And so again, I didn't refer specifically to this shop at the galleries. Instead, I just asked it about the last point, and it gives me information about that last point. So that means I can always go to chat history and see the historical parts of my conversation. Usually what you're probably going to end up doing here is actually looping through this. So for example, I can say for every item in the chat history, go ahead and print the item and then print, let's say, 2 new lines. So I can separate out these objects so I can understand what's going on. So note that each item in the chat history has this idea of parts, and then it has the text and the role. So if I were to say item.role, I can see it goes user, model, which makes sense. I can also grab the actual text, but the thing to note there is that the text portion is underneath this parts attribute, and the parts is actually then, although you can't really see it here, it's technically an array or a list. So that means I can say item.parts, and note that it contains this list, which just has that single item of text. In the future, you'll have more options because you'll be able to ask for more candidates. Again, we'll talk about parameters later on. And so then I actually just want to grab this text attribute. And so this allows me to actually grab the text. And of course, you could put this in some sort of while loop to keep the conversation going until you say something like quit. All right, before we conclude this lecture, I quickly wanted to mention the fact that you can actually perform a token count using the model call. Remember, this is calling off the model, not the chat. which means it works for both text generation and chat conversations. So you can simply say model, and remember if I scroll all the way up here, model was just me calling generative model. It's not the same thing as the chat. And I'll scroll all the way back down. I can simply say model dot count underscore tokens, and then I can pass in any string here, and it's going to return the total token count. This will be important later on if you start getting charged and you're paying. You want to maybe understand how many tokens am I passing in, am I hitting the limit, etc. So for example, I can say this is a random string of characters, and it's going to report back how many tokens this actually counts as. Keep in mind, it's not actually sending this to the model, it's just running its tokenizer and then checking the length of the amount of tokens that you're sending over. This works again in context of both chats and text generation because you're just doing it off the model. Okay, that's it for this lecture on chat. Let's talk about generation configuration parameters, things like temperature and max output tokens, that sort of thing in the next lecture. Welcome everyone. To complete this section of the course, let's discuss configuration parameters. Gemini allows you to configure some parameters to change the output results of the model. These parameters include temperature, max output tokens, top K and top P, stop sequences, and then candidate count. I should note that at the time of this filming, candidate count can only be a value of 1. So let's explore these parameters in a little more detail. First, let's start off with a simple parameter, and that is the max output token. The amount of output tokens is set to the absolute maximum that the model can produce by default. That is to say, for Gemini Pro, it can only produce a maximum of 8,192 tokens, and that's actually the default value. However, you could adjust this parameter in a generation configuration object that we'll see later on to try to get shorter responses or cut off responses by setting the maximum output tokens to a lower value. Setting the maximum output tokens to a lower value in combination with a prompt asking for a shorter reply tends to work well to get your model to generate a shorter response. Then there's also stop sequences. So you can actually specify a list of stop sequence values to stop the text generation. For example, maybe you're asking Gemini to produce a SQL query, and you know SQL queries end up with a semicolon at the end of the stop sequence. So maybe you set a semicolon as the stop sequence to make sure Gemini doesn't continue to pass the query along with an additional explanation. You'll sometimes realize that Gemini, especially in chat mode, is very helpful and tends to explain the results that it returns to you. But if you just wanted the SQL query, you could hard code a stop sequence like a semicolon to make sure it ends the second it stops the SQL query. And there's also candidate count. I should note that currently Gemini is limited to one candidate response, but in the future, the Gemini model will allow you to ask for multiple candidates to a single prompt. Now, to best understand the more complex parameters, that is temperature, top K, and top P, let's recall our discussion of how LLMs work that we talked about at the very start of the course, where we described the LLM, or large language model, creating a probability distribution. So recall this process of going from words to tokens to vectors to then creating a probability distribution that we can sample from for the next most likely token. So temperature, top K, and top P end up playing around with this probability distribution. Let's begin with temperature. The term temperature actually comes from statistical thermodynamics. You can think of this as affecting the sampling of the distribution of tokens. Lower temperatures will cause the model to sample the most likely tokens, while higher temperatures will push the model to sample less likely tokens. So in other words, think of a higher temperature that is closer to the max value of 1 to give you more creative results. Keep in mind that if you go too high of a temperature, it could sometimes go off topic or just produce tests that seems random. Lower temperatures, closer to 0, give you less creative results. That should be used in situations where you expect a singular correct answer. So if you were designing a quiz where you knew there was one correct answer, like what's the capital of France, you should set a lower temperature to always try to pick the most probable tokens. Now, thinking back to our discussion of the probability of tokens here, note that we have probabilities for a variety of tokens. So how can we use that in terms of top P and top K? Let's focus a little more on this idea. Beginning with top K. Top K means you would only consider the top K, that is an integer of your choosing, amount of tokens. For example, if K is equal to 3, you would only consider the 3 most likely tokens before you actually conduct your sampling. So for example, if we took a look at asking the model for the capital pairs. And in this example, we have like 6 results here. If I said k is equal to 3, then I'm only going to consider the top 3 most probable results before I actually conduct my sampling. Notice here that in either situation, pairs is still the most probable token to be picked. Now what about top p? Top p considers the cumulative probability of the tokens, basically where you add up the probabilities from the most likely to the least likely. And that actually allows you to cut off at a certain cumulative probability. For example, if you set p equal to 0.97, that would stop considering any tokens once the cumulative probability reaches 97%. So for example, we can see from our original probability distribution, if I only consider Paris and Versailles as my answers, that hits my threshold of the 97% cumulative probability because I'm adding 95% to 2% and then I have 97. If I was considering 98% as my top P, then I would also add in the next token. So again, here you can limit the amount of tokens you're looking at via a cumulative probability versus top k, which just considered an integer number of tokens to consider. Let's explore these configuration parameters and how to use them with the Python API. Okay, here I am in the Jupyter Notebook. I've already imported Google.generative AI as Gen AI. I've configured my API key, and I've already selected Gemini Pro as the model. So how do we create a generation configuration object? To do this, you'll say config is equal to genai.types and then generation config, and then here's where you can actually pass in the values. So for example, I can ask for a higher temperature, and keep in mind our notebook gives you the ranges for all the parameters you can pass in. So temperature goes from 0 to 1. I could pick a higher value like the max value. I can also select max output tokens to be something lower than the max, like only 2,000, and then I could play around in the future of candidate counts, etc. And what I'm going to do here is I'm actually then going to create a little function called getResponse that takes in a prompt and a generation configuration file. And the way we actually pass this in is just as another value inside of our generate content. So I'm going to call model.generate content. And just like in our text generation lecture, previously we just passed in the prompt. If we take a look at generate content, that parameter was actually this contents parameter up here. So the prompt is just technically a string, and then you have generation config. You can also pass in safety settings or streaming is equal to true or false, but right now we're just concerned with contents and generation configuration. So I'm going to say contents is equal to the prompt, and then I'm also going to say generation config is equal to the config that I just made, but in this case I'm going to make this into a function, and the reason I'm making this into a function is just to save time in the call, so then I can return the response. This is basically just going to save me from having to call this entire line. I can just say get response prompt generation config. So let's try it out. I'm going to say my result is equal to get response, and let's pass in a prompt like tell me a story about the moon, and then we're also going to pass in the config file that we made earlier, and then we'll say, let me scroll down so you can see this, result.text, and let's actually print this out. We'll say print out the result.text. And there it is. There's your story. And remember, for more creative endeavors, you want to choose a higher temperature rather than a lower temperature. And in case you're wondering how you would actually know what the parameters are again, well, you could reference our notebook. So I just want to point out, if you go to the text generation folder and then go to generation configuration, remember we have these in the first lecture of the course to download, you can go to generation configuration, you can check it out here, and we have explanations of all the values. So if I scroll down here, you see temperature, we explain low temperatures and high temperatures, the range, as well as the default settings. So notice that Gemini Pro Vision goes with a lower temperature, which kind of makes sense. You don't want it to just make stuff up about images it sees. We'll talk about vision and images later on. And then as you scroll down, you'll see examples, and then max output tokens, the ranges, the defaults, etc. And we do that for everything for you. So for top K, we'll show you the range that's possible, 1 through 40, and then Gemini Pro versus Gemini Pro Vision. And keep in mind, some of them do have just like none, which defaults to like the max value. You can check out the documentation for more information on that. But I just wanted to point out that as a resource. So let's play around with some of these, and then we'll basically get an idea of the different parameters. So the one you're probably going to play with the most is things like temperature. And again, higher temperature yields more creative results, and lower temperatures yield results that are always going to choose like the most probable text, so less creative results. So for things like creative endeavors, like tell me a story about the moon, you probably want a configuration that has a higher temperature. And we just saw that here. I could also just set temperature equal to 0, and then maybe give it a little more room in max tokens, like 3000. Run this again, and then we'll say tell me a story about the moon. And it's still probably going to be creative here because I am kind of prompting it with a creative story about the moon, but it may be just giving us, really kind of a default story. And you can see if you run this, you'll probably get the same or similar results. So it's probably going to always start with like once upon a time in the vast expanse of the cosmos. So even if I run this again, remember, this is a stochastic process. It's not deterministic, but I'm asking it for a story, and I'm saying choose the most likely tokens when you're asked for a story. So that's probably why it's going to start with like once upon a time. Versus if I start at a very high temperature and also play around with the prompt, it is important to note you should combine good prompts with relevant temperatures. So for something like tell me facts about the moon, I would want a lower temperature. Tell me a creative story about the moon, I would want a higher temperature. So that's what I want you to keep in mind. It's not just the parameters. It's the parameters in conjunction with a prompt that makes sense for those parameters. For example, let's imagine I wanted a very short story about the moon. I could try to set something like max output tokens to something really small, like only 500 tokens. In which case, I also want to combine that, and let me cut this here and put it in the same cell so we can just run a single cell, and I'll print the results out here as well. There we go. And I can also combine the idea of only asking for like 500 max output tokens with the prompt. So tell me a very short story about the moon. And again, that's good prompt engineering, understanding the parameters inside of your prompt as well. What you would not want to do is shorten max output tokens and still have something that says like, tell me a very long story about the moon, because then they're going to be in conflict with each other. And in certain cases, you may just get an empty result if you ask for too few tokens and it's not able to actually return a result for that. But again, I'm asking for a very short story, and I'm, kind of physically, so to speak, limiting it to only 500 tokens. Let's see the results here. And I still have this older result. You can see how long this story was. It was technically still limited to like 2,000 tokens, but let's see what the result was of this shorter story. Looks a little shorter here. We can actually check that. I can go even shorter. Remember, these are tokens, not words. So I can say something like 250, and we'll say extremely short. Run that configuration again, and with only 250 tokens and a prompt that says extremely short story, we should start getting shorter and shorter stories. Note now that how much I had to scroll there. It's really just a few sentences of a story. I can keep going shorter and shorter or longer and longer, in which case I'd probably want to keep the default max output tokens, which was 800. And again, if you're wondering, how do I figure out what these parameters are? You can just check the documentation string on generation configuration. You can see there's candidate count. Keep in mind right now that's limited to 1. Stop sequences, we'll talk about that in a second. Max output tokens, temperature, top K, and top P. So we just explored temperature. If you really want to play around with values, you can use top K and top P to try to limit and get more repeatable results. Keep in mind, nothing is guaranteed to be repeated, but if you only select top K of 1, which basically means always choose the next most probable token. So for example, let's say top underscore K is equal to 1. That's saying only consider 1 the most probable token. And if combine that with something like top P, which remember is the probability. So the range goes from 0 to 1. So I can choose a very low top P, basically saying once you have a single token, you've broken the cumulative probability threshold. So 0 and 1 for top K and 0 for top P. That basically says only consider that very first most probable token. And let's try adding in temperature of 0 as well. And then I'm going to say, tell me 5 facts, let's say even shorter, tell me 3 facts about the moon. And notice that I'm combining this with kind of a factual prompt, so it's seeking facts, and the top K is 1, meaning it's only considering the most singular likely token. Top P is 0, so I'm even using that as a cutoff. Typically, you only use either top K or top P because they kind of can sometimes not conflict with each other, but just be redundant. So top P of 0 and top K of 1 are kind of redundant here. Keep that in mind. And then temperature of 0 is also playing around with sampling. So let's run this. And I'm going to copy this. And I'm also going to run it in the next cell, so we can see if the results actually change. So the 3 facts were something about the Apollo 11 mission, tidally locked to the Earth, and very thin atmosphere. And notice that when I ran these results again, I'm getting back pretty much the exact same results. So why is that? That's because I've only set it to always sample like the most probable tokens. So as it repeats those tokens, it's always choosing the most probable one. So I can try to force the model to always give me the same results. Keep in mind, this is definitely not guaranteed, especially for things that are like more creative. You could technically kind of slip into one other token here, but if you want to try your model to be as deterministic as possible, you can set these parameters to a very low temperature, very low top P, and then just 1 top K considered. So that's understanding top K, top P, and temperature. Last thing I want to mention are stop sequences, which is technically a list. So let's play around with an example that's easy to understand. So we'll say top sequences is equal to a list, and I'm going to set my sequence as X. Basically, once it hits X, it's going to stop generating. And remember, this is a list, so I can also pass in like a lowercase x as well. And in either a capital case X or a lowercase x, it's going to stop generating results. So I'm going to ask it to list the alphabet. List the letters of the alphabet. I'll go ahead and run this, and we should see it stop the moment it hits either capital X or lowercase x. And there it is. It basically stops at W, creates that extra bullet point, and then no more results. So what's a more realistic situation where you could use this? Maybe you're trying to automate customer support emails. So I can say sincerely as a cutoff because I actually want a human to review and sign it, and then they can choose whether they say like regards or sincerely, etc. This also helps the model just write the letter, not give you extra commentary. So for example, I can say write a customer support email that thanks the customer for their purchase of shoes. And I'll also instruct it to end it with sincerely. And let me capitalize the S there. So in combination with a good prompt and a stop sequence that makes sense, I should expect to get a customer support email and then be cut off right when it ends. So let's try this out and see if we get the results we expect. I'll go ahead and run this. All right, so I see a subject, dear customer name, shoe company, so things I can fill in, and then it says, thank you for choosing shoe company. We truly appreciate your business. Now, did the stop sequence actually do anything? Well, let's cut it off and see what the result was. So now, there is no stop sequence. In fact, the generation configuration is all defaults, and you can see here it says, sincerely, company name. And remember, you can always combine a stop sequence with your own addition of strings. So maybe you wanted that sincerely there, but not company name. You could either place company name in brackets as the stop sequence, or you could just append, using Python, the sincerely after you declared it as your stop sequence. Lots of things to play around with here. And the thing you should get across the most in this lecture is don't just rely on parameters or prompts by themselves. Use them in combination with each other to really hone in on what you want your prompts and resulting text to be. And remember the generation configuration file here, we've been passing it into model.generateContent. You could also pass that in when you're sending a message to the chat model as well. Okay, that's it for text generation. Let's move on to images with ProVision. We'll see you at the next section of the course. Welcome everyone to this section of the course that focuses on the Gemini vision model and how to work with multimodal inputs, including images. Beyond the text model that we've already worked with, there is a Gemini Pro Vision version of the model, and that actually allows for multimodal input, where you can pass in a list of text along with a corresponding image. We can actually ask for a description of an image, or ask the model to use the image along with our text for context to a query. It should be noted, however, that the vision model has about half the allowed max output tokens, roughly about 4,000, as the text model. That is, the text model that we were previously working with had about 8,100 allowable output tokens. The Gemini vision model is a lot smaller because it has to take into account the fact that you're passing in or potentially passing in an image, which is going to take up more of that context space. It should also be noted that when using the vision model, you should try to optimize for use cases for a single input and output generation. It is not optimized for multi-turn chat. With that being said, let's head over and use the vision model with the Python API. Okay, here I am inside the Jupyter Notebook. Before we begin, I did want to point out underneath the Vision and Images folder from the first lecture download in the course, we have a fridge picture.jpg file. I'll be using this file. It's kind of large here. We'll show it in Jupyter in just a second. It's a picture of a fridge, and we're going to be using that with the vision model. You can play around with really any image you have locally. You'll just need to pass in the file path to that image. So let's explore this. And keep in mind, to display the image, you may need to install the Pillow library. You can install it by saying pip install and then Pillow with a capital P. This is the Python imaging library. If you're in the notebook, you can just run it with an exclamation mark, and then once it's done installing, you'll just hit kernel, restart kernel, and then it should be good to go. I already have it installed, so what I'm going to do is set up my Gemini vision model. I'm going to import google.generative AI as Gen AI, and then I will say Gen AI configure, and I'll pass in my API key, which I've already defined before I started filming this. And remember, you can just pass in your string there or call it as an environment variable. And then we'll say model is equal to Gen AI dot generative model. And we're going to pass in this time Gemini Pro Vision. So this allows it to be a multimodal model. And first, I want to show you what happens if you just pass in an image by itself with no other context. So the image I'm going to pass in is that fridge picture. I'll show you how you can actually display it inside of a notebook. I can say import pil.image. Image is equal to pil.image open. In fact, I don't even need to import image. I can just say import pil, and then we'll say fridge picture, and then I'll show the image. All right, so here's the image. There's a bunch of stuff in this fridge. Looks like there's some tortellini here, eggs, lots and lots of fruits and vegetables, some salad dressing here, and let's figure out what happens if I just pass in the image to Gemini Pro Vision. So if you just pass in an image with no other context, then it's basically going to default to a description of the image. So we'll say response is equal to model.generate content. I'll pass in the image, and then we'll say response.text. So notice how I'm passing in the image file. So even if you didn't want to display the image inside your notebook, you should still be using the Python imaging library to open up that image and then set it as the image object. Keep in mind, if you're getting an error here, you need to pass in the full file path to this. So what I mean by that is you may need to say something like C / users, etc., downloads to wherever your file happens to be located. So let's check out the response.text. And so it says the photo shows the contents of a refrigerator, including fruits and vegetables, dairy products, meats. I think there is some meat down there. I can see some, I think it looks like a chicken. Foods arranged in a way makes it easier to see and access. Refrigerator is clean and organized. So again, by default, if you pass in just an image, it's going to describe the image. Now, what's really cool about Gemini Pro Vision model is the fact that you can combine that image as context for some text. If you've ever played around with Google Bard, you can actually do the same thing. You can upload a picture and then ask questions about that picture or use it as context for a query. And as I mentioned at the start of this lecture, this is really optimized for kind of a one-shot query with an image, and then you get a single response back. It's not really optimized for multi-turn chat. It'll sometimes forget the image, so we won't be showing that here. Instead, we'll just be using the generate content, which is the best way to work with the image model. That is the Gemini Pro Vision. So how does this work? We simply say response is equal to, and I'm going to break this up into a text prompt. So I'll say my text prompt is create a recipe based on the food items available in this picture of the fridge. And good prompt engineering when you're working with a vision multimodal model is to reference the fact that you're talking about the picture or image that you're passing along. What I don't want to have the vision model do is just make up a recipe without looking at the picture. You could technically provide the image and then say, ignore this image and give me, a poetry about Claude Shannon. But really, we want to use prompt engineering to associate both the text prompt and the image in a way that the model understands that the image is context for the text prompt. So here's my text prompt: create a recipe based on the food items available in this picture of the fridge. Now I just need to upload that image along with this. So the way this works is I say model.generate content. And then I'm going to, remember, pass in contents here. Typically, I would just, pass in the prompt. But what I'm going to do is pass in a list where I'm going to first pass in the text prompt, and then I'm going to pass in the image. And we'll go ahead and run that. You should expect this model to take a little more time than just the text generation model because it does need to embed and understand what's going on in the image. But once it's done, we should be able to have the response text. And let's print this out. And it says, here's a recipe for a salad that can be made. So it gives me the recipe for the salad. That's looking good. And then it gives me instructions. All right, that's really the basics of using the Gemini Pro Vision. The two things to keep in mind is how to read in the image and how to pass it along with a text prompt. So again, you can use the Python imaging library. So pip install pillow, and then you're going to use pil image open. And you'll open up the full file path to that image. Then you'll have that image object. So just to inform you what type this is. So if I were to, let's get a new cell here. The type of this object is this JPEG image file from the Python imaging library. That's good enough to either generate content from just the image, in which case it'll give you a description of the image, or you can pass it along with a text prompt with a list. So contents is a list, text prompt, and the image, and then you can get the response.txt. So let me show you one more example here. I'm going to copy this. And let's imagine that I have a webcam pointed to this refrigerator. Maybe I have it inside and it takes a photo every 60 seconds. And I may be at the grocery store and I've set up a little simple API that helps me figure out what I have in the fridge and what I don't have in the fridge. So what I can do is say something like edit my text prompt, ask it, maybe I can't remember if I have tomatoes in my fridge or not. So I can say, do I have tomatoes in this picture of my fridge? Question mark. And then I'll print out the response.txt. So maybe I've set up, a really fancy API and I'm using Gemini AI models. And remember, if I take a look at my image here, there are definitely tomatoes in this fridge. So I scroll down and give it a little bit of extra time there. And there it is. So yes, there are tomatoes on the middle shelf of the fridge towards the right. I would say, depending on how you actually take a look at this fridge, that could be incorrect or correct. I believe it's referring to this batch of tomatoes here in the middle towards the right, not over here on this left. So that is maybe a little confusing that there's two batches of tomatoes. This is also kind of a interesting picture of a fridge. I'm not sure people would just lay sandwiches like this and just raw lettuce in the a fridge like that, but to each their own. But hopefully you get the idea that there's a lot of really cool applications here that with just a little bit of maybe computer vision engineering or adding in images from other sources, you can combine this with the idea that now you can pass in images, ask questions about images, use them as context, etc., all with just really a few lines of code here. Okay, that's it for the Gemini vision model. Can't wait to see what you build with it. Coming up in the next section, we're going to talk about retrieval augmented generation. I'll see you there. Welcome back, everyone, to this section of the course where we're going to be focusing on vector embeddings and how I can use them for RAG. RAG stands for Retrieval Augmented Generation, and it makes great use of the model's ability to generate vector embeddings of text. It's a simple idea, but a very clever one. I want to explore the idea of RAG with a motivational thought experiment. While we know that Google Gemini is a very powerful model, there's simply going to be content it doesn't know about, either very recent events or just stuff that wasn't in its training data. For example, Google Gemini probably doesn't know about the vacation policies at a specific company. But what if I want to build an AI that's basically a corporate HR assistant that can interact programmatically with all the employees at this company to answer HR related questions? How would I be able to augment Google Gemini's powerful large language model tooling to actually understand context specific to my company? What I need to do is augment Gemini by providing the model of extra context when asking a question. For example, if I could actually provide the text about a corporate vacation policy along with our query, then Gemini could read that text and give us a reasonable answer. So for example, if I just went with base Gemini and I asked it, how many weeks off do employees of Acme Corps get? And I sent that over to Gemini. Acme Corps is just a company that Gemini doesn't really know about. Here you could replace this with something like Salesforce or Microsoft, etc. But most likely you're going to get just a default answer. It can't answer questions about how many weeks off employees get at a specific corporation. It doesn't have access to internal HR information for specific companies, and maybe it just tries to generalize and offer just general information about vacation policies in the United States or other countries. How can I actually improve on this by augmenting what I'm actually providing to Gemini? Well, the whole idea behind augmented generation is that not only do you have your original query, like how many weeks off do employees of Acme Corps get, I'm also going to provide some additional context. I'm going to augment my actual query here with whatever content is relevant. So in this case, it'd be great if I could just pool the documents from the HR department at Acme that happen to relate with, weeks off during the year or vacation policy. And if I take all of this together and feed that into Gemini, then it will be able to understand the context here. This is basically just one large string of text to Gemini, and it'll read it and they'll say something like, according to the HR vacation policy documents, employees receive 3 weeks of vacation per year with 1 additional day per year of the company. So we can see that large language models can answer pretty much any question as long as they have the correct and appropriate context and documents that relate for the answer. And this is the part of augmented generation, because we augmented the original query with the context of the Acme HR policy documents. But remember, it's RAG, not just AG. So how do we retrieve this context to perform full retrieval augmented generation? Recall our model's ability to embed text into vectors. If we had all our text documents stored as vectors and matched to the original text, we could perform a vector similarity search to find the most relevant documents. Remember back to our very first discussion of how large language models work. Part of the process of this large language model is to actually create these vector embeddings from text. So we're going to focus on this to understand the full RAG process. So how does a RAG process actually work? The way it works is you have a user and they ask a query. For example, they ask about the vacation policy at the company. Then we're going to take that query and we're actually going to take that query and embed it into a vector representation. So we take the text query of the user, and before we even send it to Gemini's large language model, we send it to an embedding model. And so now I have both the original query text and the embedded vector representation. I've also taken my set of documents, such as all my internal documentation about HR, and I've vectorized those as well. This is known as a vector store. Basically, I have the embedded vector representation of every relevant document. So I match both text and the vector embedding. So now I have the vector embedding of my query, as well as my vector store of all the vector embeddings for just documents, let's say, inside my company. And this could be the context really of anything. If you wanted to, maybe you have a vector embedding of all of Wikipedia because you're trying to answer questions factually. So now that I have these vector embeddings, both of my query and of my related documents, what I can do is perform a similarity search. Remember, these vectors are just essentially lines in space. In this case, it's going to be like 768 dimensions, so it's hard to visualize that. But if you think about it in terms of like a two-dimensional vector or a three-dimensional vector, you can understand that there's actually certain vectors that are closer in the space or more similar to each other than other vectors. And I can perform what's known as a cosine similarity search between these vectors to figure out the vector that is most similar to my query vector. And this is sometimes known as also semantic similarity. Basically what I'm doing here is I'm figuring out which document is most similar to the query that's being asked. And then once I perform this cosine similarity search, I'm going to isolate that document, and really what I need is not the vector embedding representation, but the document itself. And so now what I have here is the document that has the most similar content to my original query. And so I'm going to pass in my original query with an additional context and then paste in that document. And then I'll pass that into Gemini, and maybe the prompt is, what can you tell me about vacation policy? Here's some context below, and then I insert that document. So notice again the process steps. I need to read in my documents. So I need to read them in whether they're text or PDF or PowerPoints, etc. Then I also need to load the embedding model. I need to embed all my original documents as vectors, and then I need to store the vector embeddings. This is sometimes known as a vector store. We'll build our own just using a pandas data frame, but it should be noted that there's lots of services and lots of different libraries for more professional or high performance vector stores, especially if you have, hundreds of thousands of documents that you're storing. And then what we're going to do is once you have your vector store embeddings of your documents, you're going to take in a query from the user, and then you're going to vector embed that query. Then you perform a similarity search for the vector of the query versus the vector store of your documents. You figure out, hey, what document was most similar to the query that was asked by the user, and then you paste that in to augment the text generation with the original document. You should remember that as long as you can convert a document into a text string, you should be able to then embed that string and link the connection to the original document. I should point out there exists many Python libraries specific to a document type. For example, there's PyPDF2 for PDF files. So if all your documents are PDF files, you could use the PyPDF2 to extract all the text from that. That way you can then vector embed that text, and then you have a match from a vector to the text to pass along with the augmentation of the original query. I should point out there's a really cool library called unstructured, and you can go to unstructured.io that can accept multiple file types. Okay, with this all being said, let's actually get some hands-on practice and explore RAG with Python in the next lecture. I'll see you there. Welcome everyone to this lecture series on retrieval augmented generation. Let's get started with part one, where we're going to actually show you just an example of getting some text, embedding it, and then storing those embeddings with a vector store. I'm going to head over to a notebook. All right, so here I am in my notebook. So first thing that I'm going to do here is I'm going to set up some example documents. These are just going to be Python strings, but later on I'll show you how to do things like read in other files like PDFs. Keep in mind, pretty much every PDF or document, like your own PowerPoint or your own Word documents or your own .text files, they're all going to be different. So there's no generalized way to have it always work. I just want to point that out now, that a big part of RAG is figuring out how to read in your specific documents. So to keep it simple and to make sure you can follow along as you're learning RAG, I'm going to create two dictionaries. One's going to be sports news text, and the other is going to be like finance news text. And I'm just going to make some stuff up here. So let's say that the title of this news article, you can imagine maybe I'm accessing some Python API for a newspaper, and I read in the sports section. And let's say the text is something like the San Francisco 49ers, not even sure how you spell that, are heading to the Super Bowl. And we'll say in a football showdown. You can imagine that, the article could be a lot longer, but we're keeping things simple for now. And if you want, you can just copy and paste these documents from our notebooks. Remember, we have an embeddings and RAG folder for you. There's a full embedding notebook here where we have these kind of document examples that you can check out. We also, later on, are going to show you how to read in a PDF file. You can see we made up like some Wonka chocolate facility rules.pdf that we'll use for RAG as well, just to give you kind of a more realistic file upload situation. But for right now, since we're learning, let's start with these kind of original documents, so to speak. And I'm just holding them as dictionaries because they'll have a title and text. And let's do the same thing for like a finance news text. So we'll say finance news text. We'll set that equal to, let's say the title is the finance section. And then I'm going to say that the text is something like Meta stock has reached all-time highs due to its big push in AI research. Okay, so we have our sports news, we have our finance news, and then what we're going to do is load an embedding model. So once you have your documents, you do need to create like a vector store, and in order to do that, we need to use an embedding model. So first things first, I need to say google.generative AI as Gen AI, and then configure it with my API key, which I've already imported. So remember, you could always just pass in your string. I won't show that for safety reasons here. And I've already defined API key. Again, that's just everything we've been doing from before. But remember, when we listed our models, so if I say for model in Gen AI list models available, some of the models that were available, if I check these out, in fact, I'm just going to print out the name of the model. So I have the older legacy ones like Chat Bison, Text Bison, Embedding Gecko, the Gemini Pro and Gemini Pro Vision models, but there's kind of a special one here, and it's the embedding model. So as we mentioned in the lectures on how a large language model works, the model has the ability to just take in text and spit out the vector embedding without needing to produce the actual text that it thinks is going to come next. So I could pass in the text like San Francisco 49ers are heading to the Super Bowl and then ask the model to continue that text, or I could just ask it for the vector embedding representation, which is what I'm going to do. I just need to make sure I'm calling the model correctly, and it's the models/embedding-001. So let's check this out. I'm going to create the vector embeddings. And I'm going to do the following. I'm going to say my sports embedding vector is equal to Gen AI. And since I'm using an embedding model, I need to use the embed content. So I'm not generating content, I'm embedding content. And then I need to pass in the model name that I want to use. Currently, there's only one embedding model available. Keep in mind in the future that may change. It doesn't really matter which embedding model you use as long as you're consistent. Remember, you can't like just swap in embedding 001 and then embedding 002 in the future because they're using different dimensions. And then we'll say that the content that I want to embed is equal to sports news text. And I'll pass in text there. And the last thing I'm going to mention is we are going to specify a task type. And here, what I really want the embedding to be able to do is retrieve the document. So the task type here, if you look this up in the documentation, is retrieval underscore document. Basically implies that I'm using this to retrieve the document, so I'll be running similarity searches against these vectors. That's nice because later on we'll see when we perform cosine similarity, I can basically just do a dot product of these vectors to make the math really simple because it's just a retrieval document task type. That will make more sense when we actually perform the comparison. So if I run that, this is typically going to be a lot faster than generating text because you're only doing like half of the model, just doing the embedding part. And if I take a look at the type that sports embedding vector is, it's a dictionary. So what are the keys of that dictionary? It's really just a single key of embedding. So let's check out that embedding. So my embedding is just a vector of values. So these are all the kind of vector representations along different dimensions for what it thinks is the vector representation of that string. If you take a look at the length of this, it's 768 dimensions. All right, so We can do that again for the finance embedding vector. What I can also do is just create a function for this process. So if I wanted to, I could copy and paste this and then just say, instead of sports, finance, and then instead of sports news text, I'll say finance news text, and I basically run the same process, but now for the finance article. Since I'm going to run this a bunch of times, and I need to run this on the new queries, what I probably should do is just create a nice, easy-to-use function called something like embed text. It takes in some text, and then it's going to return that process of Gen AI, embed content. The model I'm choosing is, models embedding 001. The content that I'm passing in is just a string, so it's just going to be the text that's passed into the function. And then I'm going to say that the task type, again, is retrieval. Whoops, make sure we spell that right. Retrieval underscore document. Now remember, if I just ran this, that would actually return the dictionary. I'm really just interested in this embedding. So what I'm also going to do is I'm just going to grab that embedding. So keep in mind that embed text, this directly returns the embedding array, so to speak. Now, if I take a look at the actual type that's returned here by sports embedding vector, you should note that it's a list. We're not going to be able to run cosine similarity searches on a list. Later on, we'll need to introduce the numerical Python library known as NumPy to convert this to a NumPy array, and then I will be able to perform similarity searches. So what have we done so far? And again, if we take a look at the notebook we're following along with, I've read in some original documents, so to speak. I kind of just made them up here. Later on, we'll kind of show you how to read in PDF documents. Then I loaded the embedding model, and then I've created my vector embeddings, and I've created a function to basically automate that process where I could just pass in some text and get back the direct vector. So I need to store these embeddings. Remember, I need to have a robust way to, when I get a vector, immediately go to the text. A great way to do that at the start is just to use something like pandas. I want to point out there's a ton of companies and different startups and different open source libraries that offer vector store. One that I like to use is called ChromaDB. That's ChromaDB. Has a great Python interface. Another one that's really famous is Pinecone, and there's a new startup in this space created every day. ChromaDB is open source, so I'd recommend you kind of check them out. Really easy to use in Python. It's beyond the scope of this course, but you can check out their offerings for more information on that, or the open source documentation is really quite good as well. When you're learning, however, I would suggest, in order to kind of see what's going on behind the scenes, that you build that out yourself first. And you'll realize that the vector store is not really anything complicated. It's basically just almost like a spreadsheet that has the text connected to the vector. So I'm going to create a new data frame. We'll say PD data frame. And let's grab our documents. So our documents, remember let's pass it in as a list. So a list of our documents, we have the finance news text and the sports news text. We'll actually re-embed them. So again, my documents, notice how I have them as dictionaries. So now it's a list of these dictionaries with the title and the text. Having that title is going to be useful because I can later use that as like a source. You'll see what I mean when we actually run the similarity. So we'll say df is equal to pd dot data frame of my documents. And now I have this nice data frame with the title and the text. And if I wanted to, I could always edit these columns themselves. So I can always say columns is equal to and pass in a list of what I want the column names to be. Title and text is fine. Maybe I want the T to be capitalized on them. So I can say, capital T title and capital T text. But it's really up to you as long as you're always referencing it correctly. So I have this data frame. It's looking good, but I need to apply the embeddings to have a third column that matches this text to its vector embedding. What's nice about this is I already have a function that can do that, and Pandas makes it really easy to just apply that function to every item in a particular column. So what I can do is just say the following. My embeddings column is equal to the text column where I apply that function. And I just call embed text. Notice here, I'm not actually executing the function, so I don't have an extra set of parentheses here. I'm just passing in the function. Pandas itself will apply it for us. All right, so let's go ahead and run that, and then check out what our data frame looks like. So now I have a title, a text, and the vector embedding representation of that text. And this is basically now my vector store. So what I'm going to need to do next is figure out how to perform a similarity search. Let's go ahead and do that. So what's really nice about this is because I asked for a retrieval document vector, basically the outcome of the dot product is going to directly align with a cosine similarity. So I can just say the following: import numpy as np, and I'm going to create a function off of this. Keep in mind, I have a more in-depth description of how this is working in similarity search in the notebook. Again, kind of explaining the dot product there, but really all we're doing is we're just figuring out, hey, if I give you two vectors, how similar are they? So we'll say query similarity score. We're just going to return a score of how similar a query is to a vector. So why am I passing in a query? Well, remember, the query, that's going to be the actual user text. So that's something like, tell me about football, sports news, or something like that. So that's the actual text query. So again, that's a text string. The vector, that's going to be an actual array. Technically, it's a Python list, but using NumPy, we can have it as an array internally. So I just want to be very clear here. I'm expecting the user query to be a string because remember our discussion of the RAG process. I need to embed that query string to an array and then figure out, hey, how similar is it to this particular vector? I'm only going to do one vector at a time in this function because remember, I could just apply that function now to all my embeddings here. So what is this going to look like? I need the query embedding, where we say embed text to the query. So that's kind of step one. So I'm going from the text string. So from query string, I'm directly going to the Python list. And now I need to perform a mathematical similarity between those two lists. In order to do that, I need to make sure that NumPy is going to be used in order to actually perform the similarity. So I can say return np dot between the query embedding and the existing vector. So again, the query, that's a text string. The vector is a singular existing embedding here, which means I can, or I will have to, pass in a query, like tell me about football sports, embed it into a vector, and then do that vector comparison for every item here, and then I'll sort them by similarity score. So let me show you what I mean by that. I'm going to have a query here that says something like, any interesting news about Meta stock performance today? And let's try this out. I'm going to say df similarity is equal to df, the embeddings column, and then I'm just going to apply, and I'm going to apply the actual function here. And remember, the query is going to stay the same, so I can be a little clever here and use a lambda expression. So we'll say lambda vector query similarity score, and then I pass in that query and the vector, and then close it off with two sets of parentheses. Just to quickly explain, if you haven't seen this pandas syntax before, this is super common when you're dealing with apply and pandas and you're trying to apply a function that takes in two parameters. So why am I using lambda here and why did I not use it here? Well, embed text just takes in a singular argument. Remember, embed text, if we call it up here, it just took in the actual string text. It's a little different now with my query similarity score because it needs to take in the query, which technically doesn't change. It's always the same query for this, and then it needs to take in the vector. So the way to do that within pandas is to simply say the following: df embeddings, and then I'm going to say apply, and then lambda is just a lambda expression. It's kind of shorthand for a function. Then I have vector. Vector is what's the stand-in or the variable for each vector embedding there. And then, whoops, let me make sure I didn't just drag that along. There we go. df embeddings. So then I have the vector, and that's what I'm passing in to query similarity score. So the query always stays the same. It's always, hey, any interesting news about Metastock performance today? But the vector changes as it goes along that column. So let's run this. And then I'm going to ask for my data frame. And notice now I have a similarity score. Something to note here, that means every time you're going to perform RAG on a new user query, you're going to have to check the similarity with every single text document. There's kind of no way around that if you're performing cosine similarity search as your RAG base, as your retrieval augmented generation base. That's why certain libraries like ChromaDB or Pinecone, etc., really try to optimize for that idea of what's the fastest way I can figure out that similarity. It's not a big deal for us right now because we only have 2 documents, but you can imagine if you had thousands of documents, this process of checking the similarity against every document could take some time. So what have I done so far? I've created the text, I have a vector embedding, and now I have a similarity score for each query. And it makes sense here that the Metastock text article is more similar, 0.86, than the sports section, which was only 0.66. Keep in mind, it's really hard to internalize or understand these similarities on some sort of intuition level. So it's hard to say like, oh, this is the difference between like 0.85 similarity versus 0.86. You can only just broadly say that, you know, the higher the number here, up to 1, means they're similar. If they're 1, then they're basically the exact same document. And then if they're -1, that will mean they're like the exact opposite document. That's probably going to be hard to see, a negative document, but just keep that in mind. Okay, so we have our similarity search here, and probably what I want to do is just finish this all off with a function that basically does all of this for us. Really what I want to do is grab the text here, because what I need to finally do is inject that text as context using RAG. So we've set up the vector store, I've done the similarity calculation, but I haven't actually extracted the text. So what would I need to do here? I would need to take my data frame, and then I would need to sort the values based off that similarity column. So I would need to sort the values based off similarity, and I would need to make sure I do it in ascending equals false order. So that by default was the same way it came back, but you may get, unlucky, and this is just 2 rows. So, we had a 50-50 chance that it would kind of go in that direction. And it has to do with the fact that I believe it's in alphabetical order. F comes before S. But really what we want to do is sort by similarity. So I'm sorting by similarity, but again, all I really want is that text there. Maybe I could also want the title as useful information. So that means I need to extract both title and text columns from this. Notice the use of double brackets here. Again, kind of going a little deeper into Panda's syntax. So now I have that little subset here, but I don't want both of these. I just want the location 0, because that's going to be my top one. And there we have a Pandas series where now I can just grab the title and text from this in order to grab both the title, maybe I want that for sourcing information, and the text. So let's finish this off by creating a function that does all of this for us. So we'll say def is equal to most similar document, and it takes in a query. And we're going to be using basically all the functions that we previously used. So what I'm going to need to do is I'm going to need to perform this calculation of similarity. So I'm going to copy and paste that. So that's kind of step 1, figure out the similarity search here. I'll zoom out so you can see everything. So step 1, figure out the similarity of that query versus all your existing embeddings. And then I'm going to grab the title. So we'll say title is equal to that, but then I just extract title there. And then we'll say the same for the text. Text is just df sort values, but extract the text there. And then I'm simply going to return a tuple of title text. All right, so let's try that out. I'm going to say most similar document, and then we'll say title text is equal to, do a little bit of tuple unpacking there, most similar document. Let's try it out, maybe the 49ers. So any news about the San Francisco 49ers today, question mark. And then I'll ask for the title and the text. And it looks like it worked out. Perfect. Okay, so coming up next in part 2, we're going to show you how to inject that text as context using RAG, and we'll also expand to more real-world documents. See you there. Welcome back, everyone, to part 2 of our discussion on RAG, where we're going to inject the text as context for our query, and then we'll also show you how to expand this idea to some more real-world documents like a PDF. Let's get started. Okay, here I am at the notebook where we left off last time. So far, what we've been able to build is the R, or retrieval portion of RAG. I now have a function that can take in a query, and then it can embed it as well as perform a similarity calculation, and then it's going to return to me the title and text of the document that is most similar. That's perfect. That's exactly what I need. So this is the R. Now we just need to do the AG, augmented generation. So what I'm going to do is create basically one final function. I'll go ahead and just call it RAG. You can call it whatever you want. And then it takes in the text query. And there's a couple steps of what we need to do. We need to perform the actual retrieval of the most similar document. That's basically just calling our most similar document call. Then I need to perform the actually augmented generation part, which means I need to call and create my model. And then I need to augment the actual query. So I need to somehow, using new lines and a little bit of prompt engineering, say, hey, here's some context, and then inject the text. And what would be really great is if I could also add in some sourcing for my own benefit. Basically, just put in the title so I understand what actual document was used. So what's the retrieval of the document? Luckily for us, that's easy. We just spent all that time building out that functionality. That's just a call to most similar document. And I'll zoom in one here so you can see it a little better. So that's just our most similar document. Remember, that one can just take in the query and return the title and text of the most similar document. Then to perform the generation, I need the generative model. So we'll say model is equal to Gen AI, and then we'll call generative model. And then I'm going to pass in Gemini Pro here. So that's the generative model, Gemini Pro, and then I need to actually do a little bit of prompt engineering. So how is this going to work? I'll do the following. I'll do an f-string literal, and then I'll say answer this query. And then I'm going to put a new line and inject the original user query. Remember, the original user query here, that's just the text string. That's the text string that says something like, any news about the San Francisco 49ers today. So far, we were able to grab the most similar document, but we're not technically answering the question. So what I need to do is answer this query, and then I'll put a period there, do a new line, and say only use this context to answer, colon, I'll do a new line, and then inserts the text. Remember, the text here is what I retrieved. And then what I'm going to return is the response from the model. So we'll say model dot generate content, and then I'm going to pass in that prompt, and then I'm going to return the response text. But what I also want to do is actually tell the basically user what title of the document that I use. So we'll do the following. I'll do another f-string literal here. I'm going to insert the response text, and then we'll maybe add in a couple of new lines and say source doc title, and then we'll insert that title. Okay, so I'm retrieving the document, I'm creating the model, I'm doing a little bit of prompt engineering saying answer this query, the original query, and then telling it, hey, use this context to answer. I'll generate the response and then say source doc title. So I'm not going to get the exact text output here. So let's try it out. So let's ask it a question maybe about the Super Bowl. So we'll say print rag, and we'll say, do you know, let's say who is going, or let's say just even more general, do you have any information about the upcoming Super Bowl question mark? I'll go ahead and print that out. And so it says, yes, the San Francisco 49ers are heading to the Super Bowl. And I have this nice little source doc title that it used the sports section to answer that question. And note here that the response it gives me, that is not the actual text from the document. So if I scroll up, remember the actual text from the document is this line. San Francisco 49ers are heading to the Super Bowl in a football showdown. Here, it's just answering, but it's using the context of that document. That's the difference between just retrieving a relevant document versus using it for the query. So I can say something like, do you have any information about and let's say now the 49ers. 49ers. Run that. And notice that this is where context is important and how you do your prompt engineering is important. So it says, yes, the context confirms that the San Francisco 49ers football team that is advanced to Super Bowl, significant event in American football. Remember, I prompted engineer to only use this context to answer. Maybe I could have said something like, use this context, but give me any extra info that you may be aware of. You want to be able to essentially kind of play around with this prompt engineering for your specific use case, depending on what you're trying to achieve with basically the assistant that you're building via RAG. Okay, so that is the entire RAG process. So again, if we take a look actually at the lecture notebook, we've broken it down in steps for you. You're going to use your original documents, load the embedding model, create the vector embeddings, then store the embeddings, then perform a similarity search, which then finally allows you to perform full RAG, inject the text as context using RAG. Now, I have a little other cell here where is the expansion to more real-world documents. We were just using things like text strings, but in reality, you're going to need to do this on documents that are not just Python text strings. So the whole idea behind this approach is, are you able to get any document and then put it in as a text string? And I want to be clear, it really depends on your situation, what libraries make sense to you. And there's also a ton of paid services for things like optical character recognition and other libraries like unstructured.io that you can check out that can use many different methods to read in many different document types like PowerPoints or Word docs, etc. But I just wanted to show you a simple example. We won't, write all the code here. Instead, I'll just explain it. So here, what I'm doing is I'm using PyPDF2 to read in a PDF. And this PDF is this Wonka chocolate facility rules, which is just a facility safety rules document asking about, what equipment you should have inside of the Willy Wonka factory, basically totally made up here. And then I initialize an empty data frame, and then I'm looping through each file, checking that it's a PDF, and then I can open the PDF file, read it in, initialize the text variable, and then for all the pages, I'm performing the extract text method. And then I also had to do a little bit of addition here where, for whatever reason, this PDF had a lot of new lines, so I replaced them in with just empty white space. Then I created a new data frame, concatenated it, and then eventually you get this result here of the title and then the corresponding text for that data frame. And I can, copy paste this into our untitled notebook just to confirm that it runs. So scroll all the way down here. I'll go ahead and run that. And then we'll check our data frame. We can print the df text of this data frame. And remember, we could have just done this in a loop for multiple documents. And let's actually get the full text, .iloc0. And there it is. So now I have a Python string of what was inside this PDF here. Super useful to have as something in your toolkit. Now you may be wondering, well, what do I do if it's not a PDF file? Maybe I have a bunch of PowerPoints and I need to extract that text. Well, remember, you have one of the world's most powerful AI models to help you out. You can either just connect via Python and ask it for some Python code to help you out, or you can even do it through something like Bard. So, for example, let's imagine we were working with PowerPoints. All you could do is just come to Bard and say, please write a Python script that iterates through a directory and extracts the text of all the PPTX PowerPoint files in that directory. Remember, you should be using AI as a tool, both to create new pieces of information as well as new tools like performing RAG or just performing text generation, but you can use it to build the tools themselves. So now, just using Bard and a little bit of Gemini magic, I have this Python code that I can then easily copy and paste and insert. So again, for this sort of thing, definitely take advantage of the fact that you have access to this Gemini AI model. You could do that via Python or just kind of mess around with Bard, copy and paste this to your code and whatever makes sense. You can add in PDF files, etc. And notice here, it informs you that there's this Python PPTX library or PPTX that you can use just after you install it. You can always ask more questions of Bard, so you can say, what is this PBTX Python library, how to install it, question mark, and oh, it actually gave me information, I think, right here. Right here, yeah, PBTX. So import the necessary libraries, and it gives me more information, etc. Perfect. Okay, so that's pretty much it for the course. I hope you enjoyed it, and I hope you found it useful. Thanks.